So here we have an example of the use of vectors. This is actually from the towing industry, but it works well. Number one, because they're using wire rope, and wire rope can only act in tension, which can simplify the analysis a little bit. And I'll be picky about the terminology you used in association with this, right? This is wire rope. It's not cable. Cable's something you order for the fire station. It comes in basic or premium. When we're talking about a tensile member like this that can move, we call it wire rope. So the scenario is they have a winch here that is pulling on a piece of wire rope around a pulley to this weight. And we'll say that this load here, this weight that they're trying to slide across the ground, weighs 10,000 pounds. Now the question is, how much force is it going to take to make that slide? Well, that's a product of friction. And there's a characteristic known as coefficient of friction that relates the weight of the object to the amount of force it would take to slide it across the ground. And generally it's not more than 1. So we'll use 2/3. 2/3 is a pretty typical coefficient of friction. Of course, if you had something that was really sticky, like a really sticky race car tire, you might find a coefficient of friction of 0.9 or even approaching 1. The symbol that we use for coefficient of friction in the engineering world is the Greek letter mu, which kind of looks like the Motorola M. So I'm going to say mu equals 2/3. Well, the question then is, how much force does it take to slide this weight? Well, it's 2/3 of 10,000 pounds, which means that the tension on this cable here, if we were pulling hard enough to make it slide, tension would equal 2/3 of 10,000, 6,667 pounds tension on the cable. Now, one of the things you can think about is, well, what is the tension over here? Well, because this wire rope's being passed over a pulley, and we assume for simplicity's sake that the pulley creates no friction, which would mean that the tension is undiminished. So the tension here is 6,667 pounds. Which actually I guess we could write into this blank here. Now think about what the pulley is experiencing here. The pulley is being pulled to the left with that 6,667 pound force, and it's being pulled down with that 6,667 pound force. And you could think of it as an equal and opposite reaction, right? The pulley is pulling up on the wire rope with that a force opposite to that, and it's pulling to the right on the wire rope with a force opposite to that. And so really what we're trying to figure out here is, what would it take to make whatever this pulley is anchored to slide? Well, we can redraw this as a series of vectors, and you recall that the length of a vector describes the force, and the direction of the vector describes the direction of the force. Now, to do this analysis, you need to slide the vectors head to tail. So I'm going to redraw the vectors in that configuration. So we have a vertical vector that is 6,667, and then we need to be head to tail, which means that I'm going to slide this vector here so that its head is touching the tail of the vertical vector. And again, this is 6,667 pounds. Now you could call these component vectors, meaning that we're trying to add them up, and we're trying to resolve the composite vector, the vector that is composed of the component vectors. So the composite vector is going to go from the tail of one to the head of the other, and that indicates that collectively these two wire ropes, the one pulling to the left and the one pulling down, are pulling at this kind of southwest angle, I guess you'd call it, right? So the net effect on this pulley here is that it's being pulled down and to the left, which you probably could have guessed just intuitively. So now the question becomes, well, what's the force? Well, remember that the length of the sides, the length of the vectors represents the force, and so we can use simple geometric properties such as a squared plus b squared equals c squared. So we could say 6,667 pounds squared plus 6,667 pounds squared equals, and we got to name this vector. I don't know. I'll name it R for resultant. Equals the resultant squared. Well, we can simplify that a little further because we're squaring the same thing twice, right? So we can just simply say 2 times 6,667 squared equals the resultant squared. Of course, what we're really interested in is getting the resultant. So how do we get rid of the squared? Well, we just simply root both sides. So we'll take the square root of both sides of the equation. And I can't simply untangle this because it's a product. I have to actually do the calculation before I take the root. The right side, though, is easily figured out. You just simply drop the square. We're just down to a single power. So now it's just a matter of plugging and chugging. So we use the calculator here. And if you think about orders of operation, things that happen inside brackets, and exponents trump everything else. So 6,667 squared times 2. And then what do we need to do with that? We need to take its square root. Now if we think rationally about kind of what range should this answer be in, well, if I took both of these vectors, the vector to the left and the vector going down, and I somehow was able to spin them both to the left, well, both of them pulling together would be the sum of these two numbers, right? So both of them together to the left is approximately maybe 13,500. So that would be if they were fully working together. They aren't fully working together here. So I know the answer is going to be less than 13,500. You know, on the other extreme, if I put the two vectors opposite each other, they would cancel each other out, and the result would be 0. So if I get a negative number, that's bogus. If I get a number greater than 13,500, that's bogus. It just kind of gives us some perspective. Another way to think of it is really, I mean, you have two vectors here. It's certainly not going to be less than either one of them. So even a value less than 6,667 would indicate that we've made an error. So now I'm going to take the square root of this. And the easiest way in this calculator to do that is I'll do x to the y, and I'll raise it to the 1/2 power, which is equivalent to taking the square root. And so what we find is that the force in the resultant vector is 9,420, call it 9,429 pounds with the rounding. 9,429 pounds. So, you know, that maybe is a little bit counterintuitive, but essentially you are adding these two forces. But these two forces are not directly lined up with each other. If they were directly lined up and they were pulling in the same direction, you'd get a net force of 13,500 roughly. If they were pulling in opposite directions, you'd get a force of 0, right? So if they were 180 degrees apart or 0 degrees apart, this is easy to figure out. It's when you get these intermediate angles, like this 90-degree angle here, where we have to do a little bit more mathematics to find it out. So we would find that this this force here, like the load at this anchor is 9,429 pounds. Now, just a kind of thought about if we were trying to attach to a heavy object here, how heavy would the object need to be? Well, that's a matter of friction. So if we assume that, again, this heavy object's got a coefficient of friction of 2/3, what that tells us is that this 9,424 pounds is 2/3 of the weight. So maybe I should write that out, right? What do we know? We know that the effort, 9,424 pounds, 9,424 pounds equals 2/3 times weight. Well, if we are trying to figure out weight, we need to get the W by itself, and the easiest way to do that is to divide both sides by 2/3, but of course that is going to look ugly, right? You're going to have two fraction bars. So what is equivalent to dividing by a fraction is multiplying by its reciprocal. So 3/2 times 9,424 equals W. Well, 3/2 is just 1.5. You could certainly calculate that using the calculator, but it's just a common one that we encounter. So let's punch that up and see what we get. So my calculator won't load, but I can figure this out longhand. 9,424 times 1.5. 5 times 4 is 20, carry the 2. 10 plus 2 is 12, carry the 1. 21, carry the 2. 45, 47, right? 0, add another 0, and then it's just going to be this number repeated. 0, 2, 5, 9, 8, 9. We have one digit after the decimal point. And I think we've got an error here because we should get a number that's about 15,000. So let's look. 0, 2, 5, 9, 8, 9. Nope. So here's the error. I errantly added one extra 0 to this line. So now I've realigned these, and if we add them up, we get 0, 6, 3, 11, carry the 1, 9 and 4 is 13 plus 1 more, 14,000. And then we have one decimal point. So 14,136 pounds would need to be the weight of this anchor, which again is reasonably, right? We knew it was 1.5 times 9,000 and change. So that's an example of the use of vectors to resolve a simple problem. The next thing we'll look at is a slightly more complex problem shown at the bottom of the page here, where again we have multiple lines, and what you're going to see is reduction in tension, but we're still able to figure it out.